Hello, everyone. Today we continue with Fourier Series. I'm going to just review what we did on Thursday, and then we are going to continue with Fourier Integrals, which would be the end of this chapter, chapter 1. And maybe we would get to start chapter 2. Let's see. Let's see if we would have time or not. Okay. Okay, let's start. Let's see what we did on Thursday. So we started with a function. So that was the theme of these recent meetings we had. We were starting with a function f defined on some interval, let's say minus pi to pi to r. And then we can think about extending f to all of r by just repeating the same piece. So make a periodic function with period 2 pi. So for example, if the function is something like this from minus pi to pi, you would just repeat the same thing to get a periodic function defined on all of r. The resulting function has period 2 pi. And the main question in these recent meetings was this: can we express f as an infinite series using trigonometric functions? So the question was this: can we write f of x equal to a constant a naught plus an infinite sum, a n cosine of nx plus bn sine of nx, where n goes from 1 to infinity? So that was the main question. Is this possible or not? So the first thing we did, we assumed it is possible. So first we just assumed, without knowing if it really is possible or not, we just assumed that that's the case. And then we tried to compute these coefficients. So we computed what is a naught, what is a n, what are a n and bn's. So we computed them. And what we did was not very rigorous. We did some computations, but the computations were sometimes a little shaky, right? Like interchanging the limit and integral, the infinite sum and integral, and things like that. And then we tried to make these arguments more rigorous by studying different types of convergence, right? Pointwise convergence, uniform convergence, etc. So now at this point, the question we should raise is this: suppose we have this function f, and suppose using those formulae we had for a n and bn, we can compute these coefficients a n and bn. So we would get these infinite sums. So we would have a naught plus sigma a n cosine of nx plus sigma bn sine of nx. What does it mean for this thing to be equal to f? What do we mean for these two things to be equal? First, I want to understand what does it mean mathematically. So you see, on the right-hand side, we have a sum, okay? And this sum goes from n equals to 1 to infinity, right? It's an infinite sum. Let's do something. Let's, rather than taking this sum up to infinity, look at some finite sum. Let's look at the sum up to some terms k, the first k elements, and look at this sum. Define the function fk of x to be this thing. So I would define this function fk of x to be this finite sum. So when we say, can we represent a function f by its Fourier series, what we really mean is that when k goes to infinity, does this sequence, does fk converge to the original function f we started with or not? Okay, so that's the main question. So if you look at this finite sums, we can define this function fk, and we can take a limit fk. So this question has different aspects to it. The first question is that, is fk convergence, is this sequence fk convergence or not? The second question is that if it's converging to something, let's call that limit f star, or maybe f hat. Define this thing to be the limit of fk. Suppose it's converging to something when k goes to infinity. Is that limit really equal to f? I mean, it might be another function. And then a little more technical question would be, what type of convergence is this? Is this pointwise convergence or uniform convergence? Or maybe some other type of convergence, which we still don't know. So if, assuming fk is really converging to f, what type of convergence is this? Is it pointwise or uniform, or potentially something else? Okay. So first of all, I should say the solution to the answer to this equation, these questions, is not a general answer. It's not like we can give an answer to these three questions for every function f, right? For different functions, we might get different answers to these things. So for one function, we might get that we do have this Fourier series. It is convergent, and the convergence is uniform. For another function, we might not have that. The sequence fk might not be convergent. For another function, it might be convergent, but it might not converge to the original function. It might be convergent to another function. So sometimes we should think about these questions kind of case by case about the function which we want to study, the function f. But there are a few simple things that are pretty easy to prove. I'm not going to prove them. I'm just going to state them, but it's good to know them. And that's related to how that's related to the function, if the function f is continuous or not, right? So there are different types of discontinuous functions, right? For example, I can have a function which is, well, continuous. I can have a function which is discontinuous, but it has a jump at some point. I might have a function which at some point it goes to infinity, and then on the left side, I have something finite. I might have a function which is discontinuous at a point, but as they say, it's removable discontinuity in the sense that the right limit and left limit are equal, but they're not equal to the value of the function at that point, right? There are different types of discontinuity over, even there are kind of worst kinds of discontinuity. Maybe I have a function which is equal to 0 at 0, but when the function is converging to 0, it doesn't have any limits. Maybe the function is like this. So when it's converging to 0, it starts to it goes up and down, and it doesn't have any limits. So the function is something like this. It's hard to see, but it's not converging to 0. So there are different types of discontinuity, and these things actually matter in answering to the questions we saw before, okay? So different types of discontinuous functions. So one thing to note is that if f, suppose we have a function f, if f is discontinuous at the point x0, discontinuous at some point x0, there are, as you can see, different things might happen. But there are some quantities we are interested in. So one quantity is the f of x naught. So for example, here, if this is x naught, this would be the value of f here. If x naught is here, the value of x naught would be here. If x naught is here, the value would be here, and etc. Here, if x naught is here, the value of f of x naught would be here, and the rest. The other quantity which is interesting to us is so-called the right limit of f at x naught. So limit of f of x when x goes to x naught from the right-hand side. So it simply means if we converge to x naught from the right-hand side, what would be the limit of f of x? So here we're getting closer to x from right-hand side. The limit would be equal, the right limit would be equal to the value of f itself. So here, as you can see, f of x naught is equal to the limit of f of x at x naught from right-hand side. So limit of f of x where x goes to x naught from right-hand side. In this case, when x is converging to x naught, as you can see, the values of f are not converging to value of x naught. So the limit, the right-hand side limit would be something here, which is not equal to f of x naught. In the other example, the right-hand limit is going actually to plus infinity. In this case, the limit from right side, it does not exist. And of course, similarly, the limit from the left side. Okay, we have these three quantities. Okay, now why are these things important to us? So suppose I have this function f, and suppose this function, the graph of this function looks like this. Maybe the graph of the function is like this, from minus pi to pi. Okay, suppose that's the function. Let's show that with f. Suppose I have another function which is very, very similar. It's very similar to f. The only difference is that at 0, the value of the function is different at 0. So this is the function g. So suppose on the left side, this is 1. So f of 0 is equal to 1. G is everywhere equal to f, but g of 0 is equal to 0. Okay. Now, I can compute the Fourier series of f, and I can compute the Fourier series of g. And I claim the Fourier series of these two things, they would be equal. First of all, does anyone know why that's the case? Why this claim is true? So the claim, the Fourier series of f is equal to Fourier series of g. Why is that?
Well, both of they differ on a set that the integrals don't see. Like they differ on a measure 0 set. So the integrals, when you compute the coefficients, we don't see that.
That is correct. So if you remember the formulae we had for computing the coefficients, a naught, a n, b n, they only depend of the integrals of these functions, or integrals of these functions multiplied by sine nx and cosine nx. And when two functions are everywhere the same, they just differ at one point. One point does not affect the integral at all. It doesn't have any effect. So those integrals, all of them are equal. Therefore, the Fourier series of these two things are equal. But of course, these two functions are not equal. So of course, f is not equal to g, but Fourier series of f is equal to Fourier series of g. That's a very obvious sign that it can't be true that the Fourier series of every function is equal to itself. If the Fourier series of g was equal to g, and if the Fourier series of f was equal to f, That would have implied f is equal to g, which is not true. So what is going on here? What's the problem? So as you can see, and as you can guess, the problem is at the origin, as the point 0. These functions f hat and g hat, they are not equal to the original functions f and g at 0. So what is this common value of f hat of 0, which is supposed to be equal to g hat of 0? What is that value? Is it equal to 0, or is it equal to 1, or is it equal to some other value? What's your guess? Does anyone have any guess? Some other value, the average, and some other value. Yeah, so that is, well, both of these things are correct, the average and some other value. It is indeed the case. So we had a right limit and left limit. It doesn't look at the value of function at that point, so that's the value of this common value of these Fourier series is actually equal to, so the right limit of f, which is equal to the right limit of g, plus the left limit over 2. So the right limit was 1 and the left limit was 0. So it's just 1 over 2. So it kind of, the Fourier series converges to the average, right? So this is actually a theorem, and it's an important one. Let's go back. Let's look at our function one more time. Our function here is not continuous, right? But it's continuous on some smaller pieces, right? These functions are called piecewise continuous, or sometimes called sectionally continuous. It means the function might not be continuous, but the function is made of some continuous parts. There are intervals which the function is continuous on each interval. Okay, something like that. I would say a function is piecewise differentiable if it's not differentiable everywhere, but there are some smaller pieces, some smaller intervals, which the function is differentiable there. So for example, if I look at this function, this function is differentiable from here to here. It's differentiable from here to here. It's not differentiable at that broken point, but it's differentiable from here to here. And again, we get to a broken point. It's not differentiable there, but it's differentiable from here to here, and then it's differentiable from here to here. So there are smaller pieces which the function is differentiable in those pieces. So piecewise differentiable, or sometimes called sectionally differentiable. Now, sometimes we are interested in functions like f, which they are not only differentiable, they have derivative, they have second derivative, right? You can take derivative of these functions, you can take another derivative, you can take the third derivative, and you can take derivative up to any point you want, up to infinity. You can take as many derivatives as you want. These functions are called smooth functions. Okay, like x to the n, right? Polynomials, those are smooth functions. Very similarly, we have piecewise smooth function or sectionally smooth function, which means the function again is smooth on some intervals, and then it might not be differentiable at a point, but it would be it would be smooth on some other interval, and then at some point it might not even be continuous, but at some interval it's continuous, differentiable, and smooth, and etc. Okay, so that's what I mean by piecewise smooth function. Now, going back to this average phenomena we saw here, suppose I have a function f, which is piecewise smooth. So at some points, it might not even be differentiable. Okay, it might not even be continuous. And suppose it has period, it's periodic, and suppose it had the period is 2 times a. So rather than just choosing a, I'm saying the period is 2 times a. It's better for easier for computations. Now, if you write down the Fourier series for this function, this infinite sum, this infinite series, would be convergent. Okay, is convergent. Okay, first, it converges uniformly to a function, and the limit is equal to f whenever f is continuous. Okay, so whenever f at any point, so if, for example, our function is something like this, so at all these continuous, at all these points where the function is continuous, the limit would be f. At these points where the function is not continuous, the limit would be equal to the right-hand limit plus the left limit, add them, divide by 2. Rather than writing the limit x goes to x plus, I would show the right limit with x, f of x plus, and the left limit with f of x minus over 2. So if x is continuous, these two limits are equal, right? So, and it's equal to just f of x. So we would have f of x plus f of x over 2, which is just f of x. So it converges to the average of the limit of those 2 points. So in this example, the Fourier series would be convergent. The limit would be this. On the blue side, it would be exactly on the function. At this discontinuity, the limit of f would be this point, the average. And then for this continuous point, the Fourier series would converge again to this blue segment. At this discontinuity, the value of the Fourier series would be that blue point. Again, on these other points, it would converge to the function. On this gap, it would again converge to the average point, some blue point in the middle, and then it would go to the rest. At these final points, look at the point I have on the left-hand side and the point I have on the right-hand side. The function would converge to the average of those two. So the average of this point and this point, which would be something in the middle, maybe something here. Remember, it's a periodic function. So we are going to repeat the same thing again and again. Okay. Is there any question here about this theorem? Okay, there is just one small mistake here in what I wrote. This expression is for the function which has period 2 pi in general, when rather than 2 pi when the period is 2a, this sum is not an cosine of nx. In general, it would be what it would be. It would be n pi x over a, n pi x over a, n pi x over a. Okay, so that's the theorem. Okay, let's see. What do I want to say now? Okay, so now I mentioned a few results of the discussions we had yesterday. You can prove these theorems based on the things we did. So another way to kind of know when this infinite sum is converging, it's convergent, is when you look at these coefficients an and bn, you would get a few real numbers, right? If you look at the addition of their absolute value, you would get an infinite sum. But this is a sum of just numbers, not a sum of functions. If this sum is convergent, then the Fourier series A naught plus sigma an cosine of n pi x over a plus bn sine of n pi x over a, this would also be convergent. This would converge, this converges to some function f, and the convergence would be a uniform convergence, uniformly. Okay, so we have a kind of test. If the sum of these numbers is convergent, this sum as a sum of functions, it has some variable x, so it's sum of functions, it would be convergent to f, and in the sense we talked about, it would be a uniform convergence. Okay, maybe a good example to look to remind you, let's see, do I want to talk about that? Yeah. Let's see one example. Suppose y is equal to the absolute value of x whenever x is between pi and minus pi, and then extend this function periodically. So the function is equal to absolute value of x, so it's like this, from minus pi to pi, and then after this we would just extend the function in a periodic way. So the function would be something like this. Now we can look at the Fourier series of this function. We did this before, we can do that again. So let's do it. So we want to write this thing as a sum of these terms, a naught plus sigma an cosine of nx plus bn sine of nx. So let's review. What was a naught? A naught was 1 over 2 pi integral from minus pi to pi, the absolute value of x dx, right? And that would be just the integral of this function f. That's the area under the graph of this function. Okay, what is that area? Well, it's equal to pi times pi, actually, which is pi over 2. Now, this function has a specific property. If we call this y of x, y of minus x is absolute value of minus x, which is absolute value of x, which is equal to y of x. So this function is an even function. And we know cosine is also an even function and sine is an odd function. And whenever we have an even function, if we look at its Fourier series, all these terms having sine, they would be 0, they would vanish. If I had an odd function, it would be the other way. All these even terms would vanish. So now that we know this is an even function, there wouldn't be any term bn sine. Actually, all the terms bn are equal to 0. Okay, what about an? An is equal to 1 over pi integral of f of x cosine of nx dx from minus pi to pi. We can compute this one. This would be also equal to, it's a simple integral. Let's just write down the final result. We've done this once. It's 2 over pi cosine of n pi minus 1 over n squared. Okay, and bn is equal to 0. Okay, now we have the Fourier series of this periodic function here. You have the Fourier series of this function, right? Let's take a look at the Fourier series. So the Fourier series of this function would be, let's show that with y hat would be equal to pi over 2 plus sigma n goes from 1 to infinity cosine of nx times an, which is 2 over pi cosine of n pi minus 1 over n squared cosine of nx. So that's the Fourier series of the function we just saw. Now, using the previous theorem, I told you that if we have a piecewise smooth function, its Fourier series would converge to function uniformly. We know that y hat of x is equal to the function we defined, is equal to the absolute value of x when x is equal between minus pi and pi. And it's the same on other periods. We just look at one period. And if we just look at this sum up to k rather than infinity, this would converge to our function y uniformly. But there is a second way we can recognize this fact, and it's just by this theorem here. Here we see if the sum of the absolute value of an and bn, this sum is convergent, then the Fourier series also converges to function uniformly. So let's go back. Here, this sum sigma an plus bn, well, there is no bn, so it would be just an. It would be, well, 2 over pi comes out of the sum. It's just a constant. It would be sigma absolute value of cosine of n pi minus 1 over n squared, and goes from 1 to infinity. Because cosine is less or equal than 1, well, because cosine of anything is between 1 and minus 1, what we have here is always between, well, cosine of n pi minus 1 would be between 0 and minus 2. So its absolute value would be between 0 and 2. Therefore, let's call this quantity x. Therefore, x would be between 2 pi sigma 2 over n squared and 0, right? But look at this thing. So this sum, of course, is positive, but it's less than 2 pi times sigma 2 over n squared, and goes from 1 to infinity, which is a constant times sigma over 1 over n squared. Now, probably you've seen this thing before. This sum is convergent. You can use, for example, integral tests to see this sum is convergent and estimate the value of that. So the theorem we had implies that the Fourier series we are writing, the partial parts of the Fourier series, if rather than going to infinity, going to k, if we take the limit k, that would converge to function y uniformly. Okay, is there any question here? Okay. Okay, so that's it. We can stop here for this section. We can kind of close this idea of uniform convergence and how the Fourier series converges to a function. There are a lot of different theorems. There are a lot of stronger theorems which we did not talk about here. We wouldn't need them for this course, but they are quite interesting subjects. The next sections is about operations on Fourier series. This section in some sense is trivial. So let me write down the theorems. So theorem number 1. If you have a function f of x, if you write down the Fourier series for this function, and it has, in its Fourier series, it has some coefficients a naught, a n, and bn. If you look at this other function c fx for some constant c, for example, if you just multiply the function by 2, and if you write down the Fourier series for this new function, the coefficients would be c times a naught, which a naught is the coefficient appearing in the Fourier series of f, can, and cbn. Very trivial, actually. Theorem number 2. If you have a function f, if you write down its Fourier series, let's show Fourier series with f hats. If you have another function g, if you write down its Fourier series, let's show its Fourier series with g hats. If you look at f plus g, if you write down the Fourier series, it would be f hat plus g hat. So the Fourier series of sum of two functions is equal to the sum of their Fourier series. So a question we want to think about, we know what the Fourier series is if we have a periodic function. Can we extend this theory to the case where the functions are not periodic? So suppose f is not periodic. Okay, and then the question is that can we still write down something like Fourier series? Can we still write down something like Fourier series for f or not? Okay, that's the main motivation here. That's the main question. So here, unlike the previous parts, we have a function f defined, let's say on all of R, it's R to R. And we want to see what we can do with this function. Can we do something similar to the previous parts or not? So this is where we get to something called Fourier Integral, which is the last section in this book, which we are going, the last section of this chapter, which we are going to talk about. So we know, rather than thinking of the function f as something defined everywhere, we kind of study this function step by step. So for example, if the function f of x is something like this, and it's not periodic, it goes to infinity, no period, I would kind of think about this function as limit of a sequence of periodic functions somehow. So first I would say, suppose it is a periodic function with this period. So look at this function defined only here. Okay. If I just look at this interval, I can write down the Fourier series for that. Say from minus pi to pi. And then I would say, suppose this function, rather than being defined on minus pi to pi, it's defined on some bigger interval. Minus a to a. And then I can start to extend these intervals. Okay, so for each interval, I would write a Fourier series for the function defined on that interval. And then I extend the interval, I would write down the Fourier series for this function defined on this bigger interval. And then I would keep on doing that, and I would make these intervals larger and larger. And then I kind of take limits and send these intervals to plus and minus infinity to get the whole function. So that's the idea. So it's just, the idea is to kind of estimate the function defined on all of R as functions defined on smaller intervals, which they are becoming larger and larger to cover all of the R. So if rather than thinking about the function defined everywhere, if I think the function f is defined only on this interval, I can write down the Fourier series for that, right? F would be equal to, f of x would be equal to the integral of 1 over 2a, integral from minus a to a, fx dx. This is the constant part, plus sigma n equals from n equals to 1 to infinity, an cosine of n pi x over a. What is this coefficient here? Maybe I should move it a little to right. So it would be an times cosine of n pi x over a. What is an? An is now equal to 1 over a integral from minus a to a, f of x, cosine of n pi x over a dx. This whole thing times cosine of n pi x over a. And then a very similar sum for sine. So just rather cosine, we would have sine, right? So this would be the Fourier series of this function, but defined from minus a to a. Now, what I want to do is I want to take limit and send a to infinity, okay? That's the idea. So let's see what would happen. Maybe it would be just to introduce some notation. I would define lambda n to be n pi over a, just so here, this number here we are defining, we call that lambda n. This number also appears here, lambda n. And yeah, and also let's define two other notations, a lambda and b a lambda. Define these are functions of lambda. The first one is equal to, well, it's almost what we did before. It's 1 over pi integral from minus a to a fx cosine of n pi x over a, which this part is lambda, so I would just write down lambda x dx. The other one is exactly the same thing with sine, so I would define the other one as 1 over pi integral of minus a to a fx sine of lambda x dx. Now with these notations, the Fourier series we had, the terms a naught, an, and bn, we can write them slightly more briefly. Well, not about a naught, about the other two. An would be pi over a of this number we had lambda n, and this would be pi over a ba of lambda n. There's a reason I'm introducing these new notations, because they have a meaning here. Okay, so let's just take them as definition. Now, why is that good? Well, let's go back to the function f. If I write its Fourier series in terms of these new variables we define, it would be equal to a naught plus sigma n goes from 1 to infinity, a times a lambda n cosine of lambda nx plus b a lambda n sine of lambda nx times, well, let's see, times here we should multiply everything by pi over a. So maybe I can bring everything out, pi over a. There's a coefficient pi over a. Now, we show this coefficient pi over a. Well, think about this. Pi over a can be thought of as n plus 1 pi over a minus n pi over a, right? The difference between these two, of course, is pi over a. But the first one is lambda n plus 1. The second one is lambda n. So it's the difference between two of these variables, lambda n plus 1 and lambda. And because of that, we show this with delta lambda n, right? It's the subtraction between these two variables. So rather than pi over a, we would just write it as delta lambda n. Now we can, rather than taking the limit and sending a to infinity, well, look at that. If a is going to infinity, let's see what would happen to each of these variables we have here. So for example, let's see what would happen to this function a sub a lambda. Well, this function was defined as 1 over pi integral from minus a to a, f of x cosine of lambda x dx. Why am I sending this lambda to infinity? Because this is the interval my function is defined, right? This is my function is defined on the interval from minus lambda to lambda. I want to send that to infinity, right? I want the function to be defined on all of R. I don't want it to be just defined on some smaller interval. Now, what would be the limit of this thing? Well, it would simply converge to 1 over pi integral from, well, minus infinity to infinity, right? Just a goes to plus infinity, minus a goes to minus infinity, fx cosine lambda x dx. This is still a function of lambda, so we use the notation a lambda to define this thing. So it's a, when I do not use the index a, I mean a is infinity, plus or minus infinity. So here, if I look at this equation, the whole equation, and if I take limit of that, and if I send a to infinity, what would happen here is that the interval where this function f, which this f is defined, would become all of R, right? Because it's defined from minus a to a, which would be from minus infinity to infinity. It doesn't change anything here. This thing here goes to a lambda n, which we should see what happens to lambda n too. And also, well, maybe it's better to just say this part goes to a. Very similarly, this part would go to b, right? This example is from the book. So let's f of x to be equal to e to the minus x when x is positive, and it's equal to 0 when x is negative. Okay? And let's call what we had right now Fourier integral. So write down the compute the Fourier integral of f. Okay, let's compute the integrals we had. So one was a lambda. So rather than taking integral of this, well, let's write down what the function f was. Let me remind you. So the function f of x was equal to e to the minus x when x was positive, and 0 when x was negative, right? And the idea was to write down the function f of x as a constant plus these integrals. One was, well, what was it? was the integral from 0 to infinity a lambda cosine lambda x plus b lambda sine lambda x. Here, the integral is with respect to lambda, and the definition of a lambda and b lambda was there were integrals with respect to x. It was 1 over pi integral from minus infinity to infinity, fx cosine lambda x dx. This is the integral with respect to x. And b lambda is the same thing, but we have sine here rather than cosine. Okay, so the only thing we need to compute, well, at least first, we need to compute what is a lambda here for our function f and what is b lambda, right? But note that our function is 0 when x is negative. So we don't need to take integral from minus infinity to 0. That all would be 0. So these integrals, rather than starting from minus infinity, we can start from 0, because before that, our function is just equal to 0. From 0 to plus infinity, f is equal to e to the minus x. So here, instead of f of x, I would simply write down e to the minus x. So I need to compute these two integrals. How can I compute them? Let's just do one of them. Let's just do the first one. Okay, how can I compute this integral? It's a simple one, right? What is the way to compute this integral? Does anyone have any idea what we can do here? Well, you might want to think about this one for a few minutes. How can we integrate this function? Okay, so let's follow your idea. Let's see where it would take us. What should I take as u? What is the suggestion for u? U to be e to the minus x and dv to be cosine lambda x dx. I think that's what's written in the comments. If dv is this thing, what is v? V would be sine of lambda x over lambda. That would be sine. Well, ignoring the constant 1 over pi, this would tell us e to the minus x cosine of lambda x dx is equal to uv, which is e to the minus x sine of lambda x over lambda, minus integral of v sine of x lambda x over lambda du. But what is du? Du would be minus e to the minus x dx. So here we would have minus e to the minus x dx. Minus and minus would cancel each other. But now we have a new integral, which I don't know what to do. What should I do with this new integral? Now it is very similar to the previous one, right? If I bring this constant over lambda out, it would be 1 over lambda e to the minus lambda sine of lambda x. And it is very similar to what I started with, right? Rather than cosine, I have sine. What should I do with this integral? What would be the next step?
I mean, do the same thing.
Yeah. So we just repeat what we did. We do another integration by part. So if we do integration by part for this integral, so let me just do integration by part for this one. So again, we exactly do the same thing. Now we take again u to be e to the minus x and dv to be sine lambda x dx. Now we would get something similar. We would get minus e to the minus x cosine lambda x over x. That would be the first part, minus du, which here would be minus e to the minus x dx, v, which v is also minus cosine of lambda x. Sorry, this is over lambda. Over lambda. So these two negative signs, they cancel each other. Let's see what would happen if we plug this thing back into our equation. So what we have here would be equal to it would be equal to e to the minus x sine of lambda x over lambda plus something over lambda. What is that something? The something is the part we have down here. It would be minus e to the minus x cosine of lambda x over lambda minus. So if I call this integral, I'm looking for I, this unknown I'm trying to compute. What we have here, if we ignore this lambda here, it would be again I. So it would be minus I over lambda. So it would be like this. But we should divide everything by lambda again. This is the 1 over lambda we have outside. Okay, I would erase this computation here because we don't need that anymore. I plug that into the equation. So if I call this unknown integral I, it means I is equal to e to the minus x sine of lambda x over lambda plus minus e to the minus x cosine of lambda x minus I over lambda squared. Okay. We can multiply both sides by lambda squared and take this lambda to the other side. So let's see what that would give us. Let me do that. So multiply both sides by lambda. It would give us lambda squared I would be equal to, well, lambda times e to the minus x sine of lambda x minus e to the minus x cosine of lambda x minus I. I take this minus I to the other side, so I would have I plus lambda squared I equals to lambda e to the minus x sine of lambda x minus e to the minus x cosine of lambda x. So the left hand side is equal to I times 1 plus lambda squared. If I divide both sides by lambda squared, 1 plus lambda squared, it tells me I is equal to 1 over 1 plus lambda squared times I lambda e to the minus x sine of lambda x minus e to the minus x cosine of lambda x. Now remember, we wanted to compute this integral from, well, where to where? Let's see, what are the bounds for this integral? From 0 to infinity, from 0 to infinity, because from minus infinity to 0, the function is 0. So from 0 to infinity. So this is equal to 1 plus 1 plus lambda squared. If I let x to be infinity, well, when x is going to infinity minus x, both here and here, they go to minus infinity. And e to the minus infinity is going to 0. So this one goes to 0 and this one goes to 0. Sine and cosine are bounded. They're between minus and 1, minus 1 and plus 1. So these multiplications, all of them would be 0 minus. Now, when x is equal to 0, let's see what would we get if x is equal to 0. If x is equal to 0, sine would be 0. So this one would be 0. If x is equal to 0, this is 1. We would have 1 times e to the minus 1. Is that correct? What would we get? I would get cosine of 0, which is 1, would be minus 1. It would be plus 1. That is correct. So it would be 1 over 1 plus lambda squared. Great. And what was, so if I remember correctly, there was 1 over pi behind the thing we wanted to compute. There was 1 over pi here, so it would be 1 over 1 plus lambda squared, and we also have this pi here. The interesting thing here is that the other integral is just, we can do it exactly the way we did, and we get the same answer. So it would be also 1 over pi times 1 over lambda squared. Okay, is there any question about these computations? Is this computation clear? Okay. The integration? Oh, sure. So you see, this is the function we want to integrate, right? And we did integration by part. Let me see, do you have, yeah. So we did integration by part. When we do integration by part, we should choose what is u and what is dv. We chose e to the minus x to be u, and we chose dv to be cosine of lambda x dx. If this is u, du would be this thing here, minus e to the minus x dx. And if this is dv, this would be v. We would find the antiderivative. Now, if we do the integration by part, what happens is that there would be this part, which is uv, and then there would be another part, which is v du. But this v du is kind of similar to the integral with which we started with. We started with this integral e to the minus x cosine of lambda x. Here in v du, we get e to the minus x sine of lambda x. So our idea was, let's do another integration by part just to compute this integral again. So let's take this integral and do another integration by part. So here I would take u to be this thing and dv to be this thing. So we did another integration by part. Now, the interesting thing is that when we do that, we go back to e to the minus x cosine of lambda x. So when we do the second integration by part, we end up with the integral which we started with. And I remember the first time I saw this, I was undergrad like you. I saw it in calculus course, and I thought, oh, they're going to cancel each other. But they're not going to cancel each other. So if this is the integral we are looking for, we get the same integral again in our computations, but the coefficients on right-hand side is different with the coefficient on the left-hand side. So if we multiply everything by lambda squared, and I is the integral you're looking for, the integral of e to the minus x cosine of lambda x, this would be the equation. And we can solve this equation to see what this I is. And that would be this thing here. The bounds of this integral are from 0 to infinity. We just plug in those numbers and we would get the value of this integral. Okay, great. And sure. And the other integral is, okay, I'm running out of battery, sorry. So the other integral is also similar. We can do the same thing. We should take integral, we should do it by, we should solve it by integration by parts. We should do another integration by part, just like the previous one. And then having these coefficients at hand, it would tell us that the Fourier series of f of x would be this, a constant plus integral from 0 to infinity, this coefficient we just computed, which was 1 over pi 1 plus lambda squared times cosine of lambda x, plus 1 over pi times 1 plus lambda squared sine of lambda x. Right. This would be d lambda. This would be with respect to lambda. I remember in the book it's written dx here. It's, if you take a look at the book, it is wrong. It's d lambda. Now I want to see what is this constant. A very simple way to find a constant is just to plug in some number in both sides. So let's see. Let's take x to be equal to 0. So f of x was equal to, well, let's see what would be the good value of x, for example. F of x was equal to e to the minus x for x negative, for x positive, and 0 for x negative. Now let's plug in a value of x, evaluate both right-hand side and left-hand side to find a naught. So think about this one also for 1 minute. Let's see if we can find what this constant is. So one question, this is interesting to try to work with it. Maybe we shouldn't spend much time here, but it would be interesting to see, for example, here f is 0 when x is negative. You can try to see if that's really is the case. If you, on the right-hand side, if you plug in a negative number for x, we can see if we really would get 0 or not. That is kind of interesting to see if that's really true or not. Let me just ask you something, and then we can go to the next question. One question we can raise is that if these two things again are really equal or not. So let's show the right-hand side with f hat of x. And again, what would be the f hat of 0? As you can see, f of x is not continuous at 0. So again, if the previous intuition of taking average is correct here, it should be the average of these two values. One is on one side we have 0, and the other side we have e to the 0, which is 1 over 2. So the left-hand side should be 1 over 2. Well, it's not equal to 1 over 2, but it's not even defined there. But if we want to estimate that using the Fourier series, the value we would get is 1 over 2. So again, there is this problem which we had for Fourier series. It wouldn't be equal to the function a lot of times. If you have discontinuity, it would be equal to the average of right limit and left limit. In order to answer some of these questions more carefully, a very good approach is to use complex numbers. So let's use complex numbers. So what do I mean by that? Again, let's start with the function f. Let's suppose we have written a Fourier series for that. Say we fix now the period again be 2 pi. Let's it be equal to a naught plus the sum of an cosine nx plus bn sine nx, where n goes from 1 to infinity. Okay. Now, there is a very important formula which you know, and that is this one. E to the I theta is equal to cosine of theta plus I sine of theta, right? Where I is the complex number. I squared is equal to -1. It's the unit imaginary number. Now, if I look at e to the minus I theta, it's like e to the I minus theta. Well, it means I should replace theta with minus theta. It would be cosine of minus theta plus I sine of minus theta. But that is equal to cosine of theta minus I sine of theta. Now look at these two equations, this one and this one. If I add these two equations, the addition of these two equations would be e to the I theta plus e to the minus I theta is equal to 2 cosine of theta. Therefore, cosine of theta is equal to e to the I theta plus e to the minus I theta over 2. Okay, so cosine of theta is equal to the e to the I theta plus e to the minus I theta over 2. We have a similar relation for sine. Sine of theta is equal to e to the I theta minus e to the minus I theta over 2I. Rather than 2, we should divide it by 2I. Going back to the function f of x was equal to a naught plus sigma an cosine of nx plus bn sine of nx. I can replace cosine of nx and sine of nx with these things. So it would be equal to a naught plus sigma an. Rather than cosine of nx, I can write down, well, I can bring, I guess, 1 over 2 outside. That would make things look a little more better. E to the I theta plus, I nx plus e to the minus I nx. That would be one part, plus bn. Rather than sine of nx, I would have e to the I nx minus e to the minus I nx. And then it's divided by I. But 1 over I, remember that? 1 over I is equal to minus I. So I bring this dividing by I would bring I up. So I would get minus I bn times that. Now this thing is equal to a naught plus 1 over 2 sigma. Well, something times e to the I nx plus something times to the e to the minus I nx. What is the coefficient of e to the I nx? It's an from here and minus ibn from the other parentheses. And what is the coefficient of e to the minus I nx? Again, it's an from the first one and minus ibn from the other one, which would be plus ibn from the other one. So I can write down the function f of x. Remember, this function is a real valued function. It's not a complex function. It's a function defined, say, from minus pi to r, but it can be written as a naught plus 1 over 2 sigma an minus I bn e to the I nx plus an plus I bn e to the minus I nx, where n goes from 1 to infinity. Now I can introduce some new letters here. This is common. I would define C naught to be A naught, just a different notation. I would define these things to be Cn. So Cn would be An minus IBN. So one thing to note is that what I have here is the conjugate of what I have on the other side. And a very nice way to think about it is as C of minus n. Why is that? So Cn is the coefficient of e to the inx. C of minus n would be coefficient to e to the I minus nx. So it's like replacing n with minus n. So C minus n is an plus ibn, which also happens to be Cn conjugate, Cn bar. And n goes from 1 to up to infinity. So in some sense, the first term is like positive terms, and the second one is like negative terms. I'm thinking about C minus n, okay? So I can now kind of combine these two things. F of x would be equal to a naught plus 1 over 2 sigma n goes from 1 to infinity Cn e to the inx plus c to the minus n e to the I minus nx. But you know, c to the minus n, if I break these two things, and here also goes from 1 to infinity, you know, I can do a change of variable. Rather than n, I can take minus n, so I can replace n with minus n. But what would happen is that if I do that, I should do this change of variable in the sum too. I should do it there too. So I would get, if I replace n with minus n, I would get Cn e to the inx, but then the sum n would go from minus 1 to infinity. And this one is also C naught, right? And also it's C naught times 1, and 1 is equal to e to the I 0x. E to the 0 is equal to 1, right? And as you can see, I can now add all of these things together to write this thing is equal to Cn e to the inx. N goes from minus infinity to plus infinity. So these are the positive terms, these are the negative terms, and this is the 0 term, you know, from minus infinity to minus 1, and then 0, and then from 1 to infinity. So with that notation, f of x, which f is from minus pi to r, would be equal to sigma Cn e to the I and x, where n goes from minus infinity to plus infinity. Okay, great. So Cn is equal to an minus ibn, right? And we know an is equal to 1 over pi integral from minus pi to pi fx cosine of nx, and the other one is fx sine of nx. So if we combine these two, would be fx times cosine of nx minus I sine of nx dx. Okay, so this would be the complex Fourier series for a real function. We would of course get the same results, but it's a nicer way of writing down the coefficient. Now here, cosine of nx minus I sine of nx is just e to the minus n I n x. So this gives us a better way of writing Cn. So Cn would be equal to 1 over, well, it would be equal to 1 over pi integral of fx. Sorry, there was one. Oh, this is this thing over 2. There was 1/2, which I forgot. If we look here, this is this 1/2. This is this over 2, and this over 2. I forgot that. There's a factor 1/2 outside. So an minus ibn over 2 is defined with Cn. So we do 1/2 pi fx e to the minus I n x dx. So kind of we translate this thing to a complex version of it, a complex way of writing down the same thing. Okay. Okay, let's see. Let's see if we should do an example here. Yeah, maybe we can compute one example. Well, let's see. Let's suppose f of x. Well, the simplest one. Let's say f of x is equal to x, where x is between minus pi and pi. Write down the complex Fourier series of f. Okay, try to write that down. It's a simple one. Okay, let's do the computation. Let's see, what is our function? F of x is equal to x, right? So the Fourier series of that, if I show it with f hat of x, would be equal to sigma cn e to the I n x. M goes from minus infinity to plus infinity, where Cn is equal to 1/2 pi integral from minus pi to pi of f of x e to the minus I n x dx. Okay, how should I compute this integral? Well, as you can guess by now, we mostly do integration by parts. Actually, there's a professor here at this department, Marcus Curry, and once he told me he thinks the most important thing in the whole mathematics is integration by parts. And he believes some of the deepest theorems, very deep theorems in geometry and topology, and also in physics, in relativity, in a lot of fields, there are actual different manifestations of the integration by part. We can do integration by part here too. So we can take u to be equal to x and v equal to e to the minus I n x dx. That would be dv. But that implies du is equal to dx and v is equal to e to the minus I n x over minus I n, which is just I e to the minus I n x over n. So integration by parts tells us Cn is equal to 1/2 pi u v, which is I x over n e to the minus I n x minus integral of du v, which is which I can bring this constant out, minus I over n comes out of the integral, e to the minus I n x dx. And the limits are from minus pi to pi. I would just write them here. Now, this integral, this would be equal to e to the minus I n x, again over I n, over minus I n, sorry. So the result would be 1/2 pi I x over n e to the minus I n x plus, well, let's see, I and I would cancel each other. We would get n squared e to the minus I n x from pi to minus pi. Okay, let's see what's that going to be. We should just plug in these things. So Cn is equal to, what did we get? We got 1 over 2 pi I x over n e to the minus I n x plus e to the minus I n x over n squared. Hopefully that's correct. If I made a computational mistake, tell me. So it is equal to 1 over 2 pi. Okay, let's first try it at, let's first let x to be equal to pi. It would be I pi over n e to the minus I n pi plus e to the minus I n pi over n squared minus, now the same thing for minus pi. So it would be minus I pi over n e to the I n pi plus e to the I n pi over n squared. Okay, what is each of them? What is, let's compute these things. What is e to the minus I n pi? This is equal to cosine of n pi minus I sine of n pi. Now cosine of n pi is equal to minus 1 to the n plus 1. If n is equal to 0, no, it's equal to minus 1 to the n. Minus I times 0, so it's just minus 1 to the n. So this one is minus 1 to the n. This one is also minus 1 to the n. And e to the I, sorry, I should have, yeah, that's correct. On the other hand, e to the minus, this is equal to actually e to the I n pi. We get the same thing. So this is also equal to minus 1 to the n and minus 1 to the n. So what would happen? Do they cancel each other? So I think this term would cancel with this term, and the other ones they kind of add. So we would get 1 over pi, 2 pi, and then 2 times I pi n times minus 1 to the n. Pi cancels with pi, 2 cancels with n. We would get I over n times minus 1 to the n. So the Fourier series of f equals to x, y equals to x would be sigma minus 1 to the n times I over n e to the I n x, n goes from minus infinity to infinity. One of the reasons I like these expressions, these complex expressions, more than real expressions, there are a lot of reasons. One is that I like exponential function a lot more than trigonometric function. Well, you can see that, right? I guess you like them better too, because when you have e to the x or nx or whatever, I nx or anything, taking derivative and integral of these things is a lot easier than sine of nx times something cosine of nx. So of course these things are better. The other reason is that on the other expression we had this, we had a lot of different terms plus bn sine of nx. Here we just have one thing.
I'm sorry, excuse me. Can you please go back? I didn't copy down the full answer.
Oh, the previous page?
Yes.
Yeah. Yeah, I've been told a few times. I think I'm going too fast. Sure. So I would just keep on talking then. So the other thing is that it would compactify everything. So rather than different series, we have just one. And also we had this problem of constant in the Fourier integral. This doesn't even happen here, as you would see in a few seconds. Okay. So the point is that, again, in Fourier series, just like Fourier integral, we can kind of take limits. And the same way Fourier series for real things became the Fourier integral, here the complex Fourier series becomes the complex Fourier integral, right? So here, when we have the Fourier integral, for a function f defined on all of R to R, we have complex Fourier integral. And that is just by taking limit from the Fourier series and sending the interval to infinity. Just exactly the same way we did with the real one, of course. But the point is that because now we have just one sum, everything would be there. There is no like, there wouldn't be positive terms, negative terms, and constant ones. So the Fourier integral, the formula would be this one. Because we wrote it for real ones, I would just write the final answer for the complex one. It would be the integral from minus infinity to plus infinity, a constant, a function based on this lambda times e to the I lambda x d lambda, where this function c lambda is exactly defined the way that we define Cn based on An and Bn. This is very similar. This is 1/2 A lambda minus I B lambda. And this A lambda and B lambda are the things we saw earlier, the functions we saw in the definition of real Fourier integral. Okay. Now, it's a good place to explain why this thing is important to us. I want to solve an example, just one example at least, in this 10 minutes to see an application of Fourier series. Suppose we have this ODE, the second derivative of y with respect to x squared plus derivative of y with respect to x is equal to 3x, right? And we write down, we want to compute the solution to this ODE. So the first step was to compute the homogeneous solution. I would show that with YH. The second step was to compute the particular solution, and the solution to the equation would be their sum, right? Now I want to compute the particular solution, but the idea is to use Fourier series to do that. Okay, so how would I do that? First, I would write down the Fourier series of 3x. And Fourier series of 3x is equal to the sum and goes from 1 to infinity, 6 minus 1 to the n plus 1 over n pi sine of n pi x. Great. Now I'm looking for y to satisfy this equation, but I would, rather than looking for a function y, I can look at for its Fourier series, which in general, it would be of this form: a naught plus an cosine nx plus sigma bn sine nx. N goes from 1 to infinity. Suppose there is also some extra information about the equation. Let's say y of 0 is equal to 0 and y of 1 is also equal to 0. If you remember, we call these things boundary conditions or boundary value problems. Okay, so if that's y, I can take derivative of that, right? So let's take derivative of what we have here. So derivative of y with respect to x would be, the derivative of a naught would be 0. And then we would get minus n sine of nx. That would be the derivative of an terms. And then it would be plus n bn cosine of nx, and goes from 1 to infinity. And then the second derivative of y with respect to x would be minus, this nx. It would be minus n squared an cosine of nx, and goes from 1 to infinity, minus, and then we should take derivative of these terms. We would get n squared bn sine of nx. N goes from 1 to infinity. Now, the left-hand side of the equation was the second derivative of y with respect to x plus derivative of y with respect to x, which is just the sum of these two things, right? This sum is equal to the sum n goes from 1 to infinity, something times sine of nx plus something times cosine of nx. Okay, what is the coefficient of sine of nx? There is this part minus nan, and there is the other part minus n squared bn. What is the coefficient of cosine of nx? It's nbn minus n squared an. Okay. On the other hand, this is supposed to be equal to 3x. The right-hand side was 3x, which its Fourier series was 6 over pi minus 1 to the n plus 1 over n times the sine of n pi x. So the right-hand side, the Fourier series is 6 over pi minus 1 to the n plus 1 over n sine of n pi x. Now we should let the right-hand side be equal to the left-hand side. Therefore, the coefficient of sine on both sides should be equal, and the coefficient of cosine on both sides should be equal, right? We should let these two things to be equal. Let's do that. What would we get? So the coefficient of cosine on one side is 0. 3x didn't, its Fourier series did not have cosine. So the coefficient of cosine on left-hand side, which is this thing, should be equal to 0. Coefficient of sine, which is this thing here, should be equal to coefficient of sine on the other side. And now we should solve this system of equations to find what is an and what is bn. So the first equation tells us that bn is equal to nan. I just divide both sides by n. I plug that into the second equation. So minus nan minus n squared. Well, rather than bn, I would write nan. So I would get n cubed an, which is an times minus n cubed, should be equal to 6 minus 1 to the n plus 1 over n pi. So an is equal to 6 minus 1 to the n pi times n squared plus n to the 4. I divide both sides by this number here. What is bn? bn is n times an. So it's 6 minus 1 to the n pi n plus n cubed. So what is that particular solution we were looking for? That particular solution was equal to a naught plus an cosine of nx plus bn sine of nx. The only remaining thing here, which we don't know what it is a naught. How can I find a naught? So we can just plug in some number. For example, if one part of the data, extra data we have was, we had the boundary value thing that y of 0 is equal to 0. So you can plug that into the equation and try to solve this one to get a naught. It might be a little bit, it might not be very easy, but this is something that can be done. So if you let x to be 0, these terms would all disappear. And cosine of nx would be cosine, that would be 1. These things would be 0. So, and the left-hand side is supposed to also be 0. That gives an equation for a naught. So actually we have a naught from this thing now. We can compute it right here. So therefore 0 should be equal to a naught plus sigma 6 times minus 1 to the n over pi n squared plus n to the 4. So a naught is equal to sigma 6 times minus 1 to the n plus 1 over pi times n squared plus n to the 4. So that would be A naught. So the particular solution is equal to A naught, which is this thing, plus sigma an cosine of nx, which is this, plus bn sine of nx, which is this. Where n goes from 1 to infinity and all of that. This is the particular solution. If you add this to the solution to the homogeneous part, we would get the general solution. So as you can see, Fourier series gives us a way to compute the particular solutions to differential equations, to non-homogeneous differential equations. Is there any question? So if you, this is the final answer, and this is also the way we computed it. So if not, we can end the class here. We're over time. So I will see you on Monday.